welcome to day 47. Today's episode is brought to you by the PFPA, the Pugs for Physics Association. As you can see, the physics teacher, as the course draws to a close, is getting desperate to maintain engagement. Regardless, what we're going to take a look at today is batteries. And we already know a little bit about batteries. We know that if you put batteries in series, the voltage increases. You add the voltages of the batteries in series, and a good example of that is in some transistor batteries, like this one. This is a 9-volt transistor battery. Okay. If you open it up, what you see on the inside is one, two, three, 4, 5, 6, you see 6 1.5 volt AAAs. 6 times 1.5, there's where your 9 volts comes from. When you put batteries in parallel, you have to remember the voltage doesn't increase. The advantage, of course, is that if you have batteries in parallel, each battery is supplying less current, so they last longer. And I'll tell you what, the most important thing you're going to learn in Physics 40S this year, given the climate we live in, when you jump a car with booster cables, you're connecting one battery to the other. You're basically connecting the batteries in parallel, positive to positive, negative to negative. And of course, the other thing we know about batteries is that when you hook them up to a load, their voltage drops like crazy. Like that 9-volt transistor battery in the demonstration the other day, we hooked it up to a load and his voltage output went from pretty close to 9 volts way down to 3. That's what we really want to talk about today. Why is it that the voltage of a battery goes way down when it starts supplying current to a load? Okay, so remember this, okay, that the stated voltage on the battery, whatever voltage is printed on the battery, that's the open circuit voltage of the battery. For example, suppose we have a 12-volt car battery. Well, if we take that car battery and we don't connect it to any kind of a load, if it's not supplying any kind of a current, if you just hook it up to a voltmeter, you're going to get a 12-volt reading. It's going to be supplying 12 volts. But if you hook that 12-volt car battery up into a circuit where it's actually supplying current to a load, well, then you're going to get a voltage drop. Okay? The voltage across the terminal of the batteries is going to be less than 12 volts. And the reason for that is because of the battery's internal resistance. As the electrons go through the battery, their electrical potential energy is converted to heat. Okay, now what I have over here is the equivalent circuit for a battery. If we're talking about the electrical equivalent of this car battery right here, this is going to be the positive terminal, this is going to be the negative terminal, and in between the positive and the negative terminal, basically in here, you're going to have a 12-volt source and an internal resistance. Okay? RS, that is representing the internal resistance of the battery. Now, of course, if you actually open up a car battery, it's not like you're going to see over in one corner some resistance, over in the other corner some 12-volt source, but electrically speaking, whatever is inside the car battery, this is what it's equivalent to, a 12-volt source and an internal resistance. Okay. And this kind of makes sense with this and this. You'll notice if the current is 0, and if the battery isn't supplying any current, that means there's no current through the internal resistance, So the voltage drop across the internal resistance, well, it's going to be, the current times the resistance itself, but the current is 0. So the voltage drop is going to be 0. So if you're an electron, you gain 12, but you don't lose anything. So you get to there, you just stay there, but you still got your 12 volts. But you can see that if you hook the battery up to some load where you are getting a current, well, yeah, then the voltage drop through the resistance is going to be equal to the current times the resistance itself. Then you are getting some voltage drop. So if you're an electron, you gain 12 volts, but you lose a little here. So when you get to here, well, you don't have 12 volts anymore. Car batteries, they actually have very small internal resistances. So it's not like our 9-volt transistor battery in the demonstration the other day where the voltage dropped from 9 volts to 3 volts. With a car battery, the voltage is probably going to drop just a little bit from 12 volts to like 11.9 or 11.8, something like that. All right, I think we are probably ready to take a look at an example problem. And here's the problem we want to take a look at. A 6-volt lantern battery, those big square batteries. To be perfectly honest, what's inside them in a lot of cases is 4 1.5 volt D-cell batteries in series. 4 times 1.5, there's your 6 volts. Regardless, a 6-volt lantern battery supplies 0.8 amps to a 6 ohm load. Find, for starters, how much heat the battery produces in 1 hour, and then later on the voltage output of the battery. So the first thing we should do is draw our circuit. So the first thing I'm going to do is draw the battery. Okay? This battery is producing heat. That means it's got an internal resistance inside that. So when I draw my circuit, I have to take that into account. So here's my battery. Okay? We'll say there's the positive terminal. There's the internal resistance. Now, it's a 6-volt lantern battery, so that means, it's got 6 volts printed on the outside of it. So that means that we're going to have a 6-volt source here. Whatever voltage is printed on the battery, that's the voltage source you use. And then over here, we're going to have the negative terminal of the battery. And what the battery is supplying 0.8 amps to a 6 ohm load. So the current is equal to 0.8 amps. And just like it says, it is connected to a 6 ohm load. So our load resistance, 6 ohms. Okay. And there's our circuit. Total voltage increase of 6 volts, 2 resistances in series. Yeah, this one is actually inside the battery, but in reality, who cares? And the current going around the circuit is 0.8 amps. Okay, whatever information is given in the question, it is on the diagram. And we want to find how much heat the battery produces in 1 hour. So you got to remember, it's not how much heat the load produces in 1 hour, it's how much heat the battery produces in 1 hour. And this thing right here, the internal resistance of the battery, that's what's going to be producing heat due to the battery. Okay? So how much heat does this thing produce in 1 hour? So how fast is it producing heat energy? How fast is it taking electrical energy and converting it to heat energy? We need to figure out the power of this resistance for starters. Okay, how can we do that? Okay, we've got to figure out the power of this resistance for starters. How can we do that? I'll tell you what. How about, remember there's three ways to figure out power. V times I squared times R, V squared over R. Okay. Seeing as I already know what I is, okay, seeing as I already know the current through this resistance, okay, what I'm going to do is I'm probably going to use this equation, okay, to figure out the power of this resistor. Okay, so I want to figure out the power of this resistor, and that's going to be equal to I squared times R. So you take the current through the resistor, which is 0.8 amps, you square it, and then you multiply by whatever the resistance is. So I got to figure out what the resistance is. How can I do that? Well, how about this? The total voltage increase is going to equal to the total voltage decrease. And the total voltage decrease is going to be the current through the total resistance times the total resistance of everything, the equivalent resistance for the circuit. So, the total voltage decrease for the circuit, okay, well that's going to be the same as the increase, 6 volts. The current through the circuit is 0.8 amps. The equivalent resistance for the circuit, well, these two resistances are in series, so it's going to be this one plus this one. And here we have a nice little equation that we can solve for RS. So let's take the 0.8 to the other side. It's going to go downstairs. So we got rid of that. Let's take this to the other side. It's going to become a negative. And there is your answer. Let's see what that comes out to. 6 divided by 0.8 is equal to 7.5. Take away 6. Comes out to 1.5 ohms. So RS is equal to 1.5 ohms. It's not a bad idea to write things down on the circuit as you figure them out. You never know when you're going to need them again. Okay, anyway, back here, what's the power of this resistance? Well, it's going to be I squared R. There's I squared. R is 1.5. What does that come out to? 0.8 squared times 1.5. It comes out to 0.96 watts, which is the same as 0.96 joules per second. So how much heat does this battery produce in 1 hour? Well, it's producing heat energy at the rate of 0.96 watts. It's producing heat energy at the rate of 0.96 joules per second. So how much heat energy is it going to produce? Well, it's producing at the rate of 0.96 joules per second. So you multiply by 60 seconds in a minute. You multiply by 60 minutes in an hour. And there's how much heat the battery is going to produce in an hour. 0.96 times 60 times 60 again comes out to 3,456 joules. Done. All right. So part A is finished. Now we will move on to part B. Okay, so now what we want to find is the voltage output of the battery. In other words, if you took a voltmeter and you connected it across the positive and the negative terminal of the battery, what voltage reading would you get? That voltage right there. That's the voltage output of the battery. Now, imagine that you had a voltmeter and it's connected here and here. Well, if instead of connecting it up between here and here, suppose you connected it up between here and here. Well, there's no potential drop through a conductor. There's no voltage change through a conductor. There's no voltage change through the conductor. So the reading here is going to be the same as the reading here, which is going to be the same as the reading here, which is going to be the same as the reading here, which is essentially the voltage across the resistor. So the voltage output of the battery, that's going to be the same as the voltage drop across the resistor. What is the voltage drop across the resistor? Well, that's going to be equal to the current through the resistor times the resistance itself. And what do we got? The current through the resistor is 0.8 amps. The resistance itself is 6 ohms. 6 times 0.8 is 4.8 volts. Done. The voltage output of the battery is going to be 4.8 volts. Okay. Quick check of our work. Quick check of our work. Okay. Remember, whenever you are dealing with a circuit, you can usually figure whatever it is you want to figure it out. You can usually figure it out two ways. So we're going to do a quick check of our work here, make sure everything checks out. Okay. How about this? How about this? What's the voltage drop through the internal resistance? Well, the voltage drop through the internal resistance is going to be the current through the internal resistance, 0.8, times the internal resistance itself, which is 1.5. And that's going to come out to be, that's like 80% of 1.5. It's going to be like 1.2 volts. So thinking about it, you're an electron, you gain 6, you lose 1.2 here. That means when you get to here, you got 4.8 left. So the output voltage of the battery is going to be 6, take away 1.2, which is going to be 4.8 volts if you calculate it that way as well. Again, don't forget Kirchhoff's first law, the voltage increases are equal to voltage decreases. You gain 6, you lose 1.2 here, and remember these two voltages are the same, so you lose 4.8 there. Your total decreases are equal to your total increase. All right, good enough as far as examples are concerned. You are now ready to get turned loose on the assignment. Couple short little topics tomorrow and the next day, and don't forget on Friday you are going to see your test on this unit. It will be quite a bit shorter than most of your other tests. It's basically going to be the exam questions from this unit instead of a regular test. Bye for now.